Okay, that's my bit of introduction and comments. I'd like to welcome Professor John Bryant back for this course. John has been with us a number of times. He's no stranger to these courses. He's the Professor Emeritus of Cell Biology at Exeter University. He's been involved a lot in setting up courses in bioethics, both in his own university and indeed in other universities around the country, and is certainly very well qualified to speak to our topic this morning, which is how far do we go in genetic engineering. So thank you very much.
So genetic engineering, how far should we go? My interest is practical and professional. That way back in the early days of plant genetic engineering, when we were evaluating what was going to be the best vector for plants, I was working with the John Innes Centre. We rejected a particular virus as a potential vector, but got a publication out of it in a top-rated journal. I'm sure Keith would agree with that as the editor. And then later, also still looking at the practicalities of plant genetic manipulation, we elucidated further the mechanism by which the chosen vector works. And then down in the bottom, we've got two illustrations of how we use genetic engineering in our research. And so the green fluorescent protein is lighting up a plant nucleus into which we have put a transgene, in other words a foreign gene, and over on the right we have been fiddling about with the promoter, the on-off switch of a gene, looking at which bits of the on-off switch were essential for activity, and the deeper the blue on the right, the more active that on-off switch was. So you can see that both in terms of the applications of GM in plants and using it as a research tool, which many of us here have done, we've been very much involved in my group in doing that sort of stuff. But it's actually not about plant genetic engineering. I'm going to talk this morning, as we'll see as we go through. So this sort of topic, the applications of science, and particularly the applications of science with which some people are uncomfortable, leads us to ask some questions of a more general nature that are not themselves scientific. So there's this idea of science and society. How should wider society make use of scientific knowledge? And C.S. Lewis, writing very prophetically in The Abolition of Man back in 1945, after the bombing of Nagasaki and Hiroshima, talked about scientific advances, both providing the Roman general with his triumph and imposing upon the prisoner in chains behind the chariot, that it did both to us. It made us triumphant, and it also made us a prisoner. Science had spoke, if you like, with a forked tongue. So how should wider society make use of genetic knowledge in this particular instance? And that leads us straight into ethics, and I'm going to unpack ethics a little bit more in a few moments' time. But this is the classic Jurassic Park question. If you remember the very lugubrious character played by Jeff Goldblum, wonderfully played by Jeff Goldblum, and his line is, you know, you guys spent so much time thinking about what you could do, you didn't think enough about what you should do or shouldn't do. Are there limits to the use of scientific knowledge? And I'm going to throw out a lot of questions and not provide too many of my own answers here. This is supposed to be thought-provoking for a Sunday morning. And then science, ethics and religion. We often hear people of several different religions saying that their ethics is based on their religious faith. And I'm going to throw out the challenge to you. Whether you're Christian, Jewish, Islamic, Hindu, how would your religious faith help you make decisions in this area of genetic engineering, about which the Holy Scriptures of Islam, Judaism, Christianity, Hinduism have no word to say? How do you use your faith, if that's what you're saying, to make those decisions? Tied up with this are wider attitudes to science out there in society, both secular and sometimes religious-based. What are general attitudes to science? And that leads in general to questions like, are there limits on the types of work we should do? Not just the applications, but are there areas of knowledge we should try to exclude from scientific? Or should limits be placed not on the sort of knowledge we gain, but the way we gain it, and what we do with it. And if I can give you an example on limits and the way we gain it, the sorts of experimentation carried out in Nazi Germany we would all regard as being ethically off limits, even if we believe human genetics is a legitimate field for study. And what about blue skies research? You know, is it okay just to research and just find out what there is there? So that's all part of the same set of questions. Okay, so attitudes to science. So these guys up on the left, you know, very sinister looking lots. Whereas down here, these guys down the right are so clean and squeaky clean that they clearly never done any science in their lives. The bottom right one was taken from the website of a well-known pharmaceutical company, you know, showing the excellence of their products. And I'm glad they've got a female actually doing the science. That does make a change, I'm glad to say. But, you know, does science lead us to a utopia or a dystopia? Do we regard scientific advances with praise, or are we suspicious about them? Are we wedded to modernity and progress and leading to progressivism, or do we have a postmodern attitude that says, well, it might be right, it might be wrong, I'm not sure about this. So there are a whole mixed bag of societal attitudes mixed up with our ethical discussion of science. So what are the issues in genetic engineering? Well, here's one of them. There's a striking mismatch between the traditional concern of regulators with issues of risk and safety and that of the public, which centres on questions of moral acceptability. So we've got two strands to our ethical decision making. There's risk, and there's the idea that in some way the techniques that we're talking about might be morally unacceptable. And that was from the Biotechnology and the European Public Concerted Action Group, which is basically anti-GM, but that's an interesting point. That is risk and the main ethical issue, or are there others? And that leads me to ask us as a group, are these part of our moral acceptability discussions? Risk analysis, risk versus benefit, precautionary principle. Do they enter into our ethical decision making about anything in science? And so a bit of ethics. I'm not going to ask you whether you obey the speed limit, but I just want to introduce the different sorts of ethical frameworks. And if I ask people why they obey the 30 limit, because I assume you all do, you know, this is, I wouldn't assume this necessarily with other groups, but you know, here I'm expecting. But if you ask people why they obey the speed limit, you can actually start to tease out the main ethical frameworks by which people make decisions about right and wrong. And we can move on then to them. Deontology, duty-based, Kantian ethics. And so anybody who says I obey the 30 limit because it is the law is saying that's a deontological system. And quite often today, since the Second World War, it's phrased in terms of rights and duties. That it's my duty to look after your human rights, it's your duty to look after my human rights. But these are black and white rules, and Kant was very clear on this. Kant, for example, believed it was always wrong to tell a lie. Always. Because if people told lies, trust would be eliminated. So that's what we mean by deontology. Absolute rules. And then there's consequentialism, which is results-based. We look at a course of action and think, will the outcome be right or will it be wrong? Will it be good? Will it be bad? This does assume we have some criteria for deciding between right and wrong and good and bad, but nevertheless, that's the basic format. And so somebody who says, well, if I drive too fast because I might knock a child over, I don't do it because I might knock a child over, they're basically working on consequentialism. It will be wrong, the outcome will be wrong. And then the third main method is virtue, which is basically saying that good moral decisions are made by people of good character. And Aristotle, although he was a natural, I'll come to natural in a minute, Aristotle outlined some of the virtues that enable people to make the right decisions, and that was very much expanded by Thomas Aquinas, and then in more recent years by Alistair MacIntyre, Tom Wright, and a number of other, Stanley Hauerwas, all suggesting that the appropriate ethical framework is actually one based on virtue, the development of good character. And we can list the virtues. And if you're a Christian thinker here, just think of the list of the fruit of the Spirit in the book of Galatians, where Christian character is outlined for us. And Tom Wright is now suggesting that developing those enables us to come to the right decisions. And then Aristotle also proposed that natural law should come in, that we should act in such a way that whatever we were dealing with was enabled to express its telos, its reason for being. And that didn't matter whether the thing we were dealing with was a stone, or an animal, or a human, or God, this basically the logos behind the universe. That any level of existence had its own telos, its own reason for being, and natural law was acting in accordance with that telos. And Aquinas picked it up as well. And I suspect that actually the Roman Catholic doctrines on contraception and so on are very largely based on a natural law interpretation, quite often based on Thomist thinking through Aquinas. So those are the kind of four main areas, but we don't come across natural law these days all that much, except in the kind of throwaway lines, like it's not natural, it should be banned, which is a kind of bastardization of natural law. What Mary Warnock calls the pub boar's approach to ethics. That's not natural, it should be banned, I don't like it. So, if we have an ethical framework, if we're working to an ethical framework, how far do our moral boundaries extend? Ethics has evolved, been derived, been given to us, whichever you like to say, in order to enable humans to get on with each other, for societies to function, for different societies to function alongside each other. That's basically what ethics is about, human interactions. But the question then comes is, how far out past human interactions do we want to extend our moral boundaries? And Jeremy Bentham was one of the first to suggest that they should be extended out to animals, for example. I'm not going to talk much about animal ethics, but that's just an example of how we might extend our moral boundaries. In the particular cases we're going to be thinking about today, the big question is, are early human embryos within our moral boundaries and therefore subject to whatever ethical system we're applying, or do they lie outside? And that's going to be, I think, a divider as we discuss some of the things later on today. Now, medical ethics has its own way of dealing with these issues, and these are what I call the four pillars of medical ethics, laid down by Childress and Beecham, or Beauchamp as I will try to call him, but he's an American, so he's calling himself Beecham. Beneficence, doing good; non-maleficence, not doing harm; autonomy, giving your patient the honour and respect due to another human being; and justice, treating everybody the same, whether it's the homeless person off the street or the woman from the big house up the road. The GP treats them the same. So these are the kind of four ways that medicine is applying whatever ethical framework it is. And I think that medical ethics is largely a virtue system, because a doctor has to use the virtue of wisdom in order sometimes to balance out conflicting ideals. For example, in beneficence versus non-maleficence. A treatment can do good, but it can also be risky and do harm. Sometimes justice is extremely hard to administer when resources are limited and funds are limited. And that went way back to Bernard Shaw's The Doctor's Dilemma.
Sorry, can you say something about the autonomy?
Autonomy has actually rather become a fairly major issue in medical ethics today, but autonomy simply says that you, my patient, are a fully fledged human being with your own rights, with the right to refuse treatment, with the right to make choices about your treatment. And in fact, autonomy is, in the individualistic society in which we live, has become actually an overriding factor in many areas of ethics, not just medical ethics. I'm sure our medical friend, was that how it works, do you think?
No, I think you're absolutely right.
Yeah. So let's go back to genetic engineering. Here are the early days. The very first paper that heralded to the world that genetic engineering was possible was when this group of Californian scientists made a plasmid is a piece of DNA that bacteria carry in addition to their own main chromosome. And what these guys did was they constructed a plasmid with an extra gene in it that had come from somewhere else, and they showed they could get it to work in a bacterial cell. So that was the first time that genetic engineering had been reported. And when we think about where we've got how far we've got in not very long, it's amazing to think that it was just 40 years ago that experiment was done. And almost immediately, some of the practitioners of this art realized that actually we could use this in ways that weren't helpful, that might be unethical, that might lead to harm. And so there was a pause. Berg, in particular, who later went on to make comments about human genetics, Berg in particular raised concerns that the artificial DNA molecules that we could make could be used in harmful ways. The biological hazards they were thinking of were mainly to do with generating superpathogens for placing, for example, genes encoding toxins into bacteria that the human frame would normally regard as friendly, that sort of thing. So new ways of infecting people. But they also raised the question, but they didn't really discuss it in any depth at all, but were there any intrinsic moral objections? Were there moral objections? Is this right or wrong? Deontologically, is it right or wrong to do genetic engineering in a right or wrong sort of sense? And a conference was called in the late 70s in California. There would have to be in California, where else? And basically a list of rules was set out. They were mainly based on risk analysis. There was very little what I call actual moral debate. So there were very few ethicists at the conference, but there were lots of lawyers. That might reflect American society, but a whole lot of regulations were laid down for different sorts of genetic engineering, depending on where the gene came from and what you were putting it into. And they covered the range, you know, sort of bacteria to bacteria, virus to bacteria, bacteria to virus, plants, animals, the lot. Even though plant and animal genetic engineering had not yet been invented, scenarios were laid out in order to make regulations. And essentially, that framework, although it has been diluted a lot because it was very cautious, that framework remains, for example, the framework that the Health and Safety Executive here still uses to govern genetic engineering experiments in government, private and university labs. It is, say, very, very much diluted now because the early framework was too cautious. But as I say, the idea of morality only barely entered into the actual discussions, even though it had been raised. So if we move on, animal cells were first genetically modified in the mid-70s, and human insulin, produced in genetically modified bacteria, was first achieved in 1978 and very quickly went to market. And we've reached a situation now where newly diagnosed insulin-dependent diabetics are almost routinely offered human insulin rather than the formerly prescribed pig insulin that had been most widely used up until then. So, you know, insulin is no longer extracted from the slaughterhouse, but is grown in 100,000 litre fermenters by Eli Lilly in New Jersey. And if you think about how much they're producing, if you think that every Miller solution has got millions of bacteria in it, and they're doing 10 or 100,000 litres at a time, that's really quite a lot of insulin. And then plants, whole animal genetic modification in 1980, so it became possible to change the genes of an animal in such a way that it carried those genes into life. And then plants in 1983. And then the most recent development has been synthetic biology, which culminated, no, it didn't culminate, it resulted in, just a couple of years ago, in a new cell being made. And I'm going to talk about that in a few minutes, because it raised quite a lot of interesting debate. So, microorganisms, I'm just going to rush through this. Very rapid take-up in research and industry, and many of us in research labs use microorganisms to basically store bits of DNA in, and we can then grow them up again. It's embedded in the pharmaceutical industry. Many products that are available for human and animal health now are made through genetic manipulation. Only a couple of vaccines so far, but many other therapeutic products. And it's very well regulated. As I say, there's a framework that is based on the original Salamar guidelines, but it is very well regulated. And then in microorganisms, we've now got synthetic biology, which is mostly being applied to microorganisms, with the thought that it might be applied to other types of organism later. So this is really an extension of, well, I've called them genetic modification techniques because that's now the terminology widely used. Genetic engineering went out of use because it had apparently a sinister kind of ring to it. So it's now called genetic modification. So synthetic biology with microorganisms is really an extension of what I would call regular GM techniques, except we can now make synthetic genes. So we're not moving a gene, a piece of genetic information from one organism to another. We can actually build genes in the lab, base by base. And that leads to the idea then that we might one day make synthetic life. And I want to explore that for a few moments now. So back in 2010, these were the sorts of headlines that were going around the paper when Craig Venter, a very well-known biotechnologist, very able, very wealthy, to give you some idea of the wealth of his organization, once the Human Genome Project had got going and he could see that there were dollars involved at the other end of the tunnel, his company bought 300 DNA sequencing machines. And they were by far more expensive than they are now. So 300 cost him quite a few $1 million then, it wouldn't now. So Venter is a larger-than-life character. Sometimes in the field we call him Darth Venter. But these are the sort of headlines that were bandied around, or we heard on the radio. American scientist creates life. Cynthia, that was the name of his cell. God O2. I bet he loved that one. Life O2. Playing God. Well, playing God is often thrown at us scientists, so that was not a new one. But that was the sort of thing that we saw. So what had he done? What had Venter really done? And that tells us what he'd done. He created a bacterial cell controlled by a chemically synthesized genome. And I'm going to unpack that a little for us so that you can think about what that actually involved. This is what he did. There are two species of a small bacterium called mycoplasma. Mycoplasmas are the groups of bacteria that are, for example, involved in some forms of TB. And there are two species which are very similar. They have small genomes, so they've got between 600 and 1,400,000 base pairs. So these are small genomes compared with the human genome that we heard about earlier. And these have approximately the same number of bases. They're just over 1,000 bases. And so what he did was he took one of those species, and destroyed its genome. Basically destroyed its DNA. And there's a number of ways of doing this, and the technicalities don't need to worry us. And then he synthesized the genome of the other species in the lab and put in an extra genetic marker so that he could tell that it was the artificial chromosome that was going to be used. So there was what we call a genetic tag, like a hashtag in some ways, but he could tell with that marker that the DNA had gone in. That was remarkable. It was the longest piece of DNA ever synthesized in vitro. And that DNA was then placed into the empty cell of the other species. So here's an empty cell of one species and the artificially synthesized DNA of the other species with the genetic tag on it. Put that in there and see what happens. And the cells took up the DNA and grew as if they were the donor species. So the whole genome worked and sustained the normal life of that bacterial cell. They grew in culture very nicely, created cells. But did they create life? Which is what the claim was. And the answer is no, they didn't. They did on a major scale what had been previously achieved on a minor scale. They did some genetic engineering. But the cell was a requisite before they could start the experiment. They did not create a cell. They changed the genetic makeup of a cell. They did not create a cell. Now, it was made, this is a little sort of a cartoon, and I've put the genome as a little blob because it's easier than putting lots and lots of curly strands. So there's the first species of mycoplasma, the top, and we're going to use UV light or laser or whatever it was they did to destroy the DNA, and then this artificially created DNA from the other species is popped in, and it was, as I say, the longest piece of DNA ever made by chemical synthesis. Very, very clever. When you read the details of the technology, very clever indeed. One salutes them. But it wasn't the first piece of DNA to be, the first nucleic acid to be made artificially. I'm going to go back to the 1960s, and here's Robert Holly, who won the Nobel Prize for elucidating the structure of transfer RNA, and they made it in the lab. And that happened when I was a postgrad. So being able to make DNA in the lab, or RNA in the lab, actually goes back quite a long way, but it was very tedious then. Don't you love those kind of 60s scientists? So what would that synthetic biology lead us to? Well, we can already see you can make novel genes. You can build a gene to make a protein of your choice. And those proteins might be novel proteins. We can, as we heard yesterday, we can use different protein building blocks. The protein building blocks are called amino acids. We can incorporate different amino acids into a chemically built protein. But the trick would be, can we get a gene to put other amino acids into such a protein? Can we code for all these strange amino acids that are out there on meteorites and out in the world? And to a limited extent, the answer so far is yes. That some of the more redundant transfer RNA molecules now can be used have been modified so that they will pick up these strange amino acids and put them into proteins. And so we can, to a limited extent, genetically design a protein with strange amino acids in, as well as designing proteins with conventional amino acids in, novel proteins and novel genes. And if you want to look at that, look at Neumann's article in Feb's Letters earlier this year. It tells you all about how novel amino acids have been coded for by modifying transfer RNA molecules. Be a bit technical. Now this has got many beneficial uses. Pharmaceuticals, for example, making drugs, industrial enzymes and proteins for processing, for example, in the food industry, and bioremediation, cleaning up pollution, whether it be oil or whether it be something that's left over from the military use of land, like hydrogen, this sort of thing. So that's the sort of potential. But again, this clearly, just like the original genetic engineering, has got these ethical issues around it. It could be very readily misused. And here we're talking about probably a more powerful tool than the original genetic engineering. So how far should we go? So this raises more discussion points. Does synthetic biology raise any issues not covered by conventional GM, or is it just a question of extent? Are we talking about the same sorts of issues, but they have a broader reach? Do we have concerns? Does an audience like this have concerns? Should we have concerns about misuse? Do we need new regulations? And again, throwing out that challenge, are people of faith especially concerned about this, or are they not? And if you say that people of faith are, then I would like to hear particular reasons for feeling that. And then, supposing life was created, supposing way down the line, deep into this century, somebody actually did create a cell, would those of us of faith be challenged by that? Would we believe that humans were indeed playing God? You can pause to think about that. Okay, let's move on to animals now. I'm leaving microbes behind, and with animals there was a very big play that we might be able to make pharmaceutical products in milk, and certainly way back in the late 1980s, blood clotting factors had been produced in lactating sheep. And Dolly was cloned partly because her clone donor, her DNA donor, was a sheep that had been modified in this way. And mammalian genetic modification is not as straightforward as bacterial. And so if you've got a transgenic animal, a GM animal, that was doing the job you wanted it to do, producing a lot of the stuff, then you might as well clone it. And so actually Dolly was a clone of a genetically modified sheep. And there was a very big, there was a large expectation that we would see farm animals used in this way in a very large scale. And people talked about, the world need for factor 9 blood clotting factor could be met by a flock of 45 lactating ewes. That's the sort of figures put on it. But actually, it took a very long time to come to market because of safety concerns, and it turns out not to be the commercial panacea that companies thought it was going to be. Not on a huge scale, but rabbits and goats are being used commercially to make pharmaceuticals. So there's a way that animal telos has been diverted in order to make things for us. And then we've got a very wide range of use of GM animals in research, mostly mice. So changing the genetic makeup of a small mammal with a gene that has an effect in human disease is very, very wide use of animal GM. Oncomouse carrying an oncogene, a gene that causes cancer. Cystic fibrosis mouse, etc., etc., etc. And then we can look at gene function by knocking out genes, by turning them off or removing them, different ways of knocking genes out, and looking at the function of that gene in the knockout. Or we can overexpress it and looking at the function when too much product is made. And as we stand here, as you sit here, thinking about Britain in general, somewhere around the country, and some of them are here in Cambridge and some of them are in Exeter, and lots of them are in Oxford, there's about 3.5 million GM mice kicking around the country, and there are others, much smaller numbers of rats, rabbits, sheep, goats and fish, but all being used in this sort of research. And so this has both pure research and commercial applications, because the commercial applications we hope will lead to treatments for particular genetic diseases as we learn more about them. So what are the ethical issues here with animals? Let's stop and think about that. I'll give you a kind of piece of scenery to look at while you think about it. We're talking about animals now. We've moved up the scale. Jeremy Bentham thinks they come within our ethical remit. I'm not going to ask you to come back at me. Just sort of pause for a moment. Right, that's enough pause. So, is it okay to use animals as commodities? Well, we do. We have used animals as beasts of burden, providers of food, for thousands of years. The question is this form of commodification any different from eating sheep, for using oxen to plough, etc.? So that's the question. Does moving a gene from one species to another offend telos, the reason for being of a species? There's at least one theologian who would criticize animal GM on those grounds. And then we have, if you like, quite a new age approach to this. But are we in some ways creating chimeras? How many human genes does it take in order to turn a sheep into a sheep-human hybrid? And even if it's only a handful of genes. And there's a kind of reductionist view that many of us scientists take. No, these are only 3 genes, to a much more holist view that suggests that actually we are in some way creating a chimera. And some of you may think that. So those are the sorts of issues that have been raised in relation to animal genetic engineering. And again, if we are people of faith, does our faith inform us or help us here? Okay, so what about humans? Well, genetic engineering of humans, as we have heard, and as I'll say again in a couple of minutes, actual genetic engineering of humans is illegal in most countries where there is an ethical and legal framework. But nevertheless, what we are allowed to do is to use genetic engineering of the somatic cells, the cells that are already here in the body, to rectify usually a genetic lesion in those cells. That's called somatic cell gene therapy. And the most successful application of this has been for severe combined immunodeficiency. That is where somebody's immune system is so poor that they go down with absolutely every passing pathogen. And the baby has to live in a sterile bubble, the boy in the bubble syndrome. And by genetically modifying the bone marrow, it has proved possible to cure that. Now, it's quite a rare condition. And as of last year, some 15 children in Britain, and a similar number in France, and I haven't got the data from America, have been cured of this condition. And certainly the oldest child cured of this condition in Britain via the Great Ormond Street labs is now well into primary school. unable to cope with all the kind of pathogenic insult that being at school brings upon you. So it is successful. And indeed, of all the cases I know from Europe, only one has been unsuccessful in terms of restoring immune capacity. On the other hand, a small number of patients, the transfer of the correctly functioning gene into the bone marrow has activated an oncogene causing cancer. So in a small number of patients, about 25% in Paris, and rather fewer in Britain, a child has gone down with leukemia. The leukemia in each case has been put into remission, in other words the child has been cured, but it's quite a big price to pay, but maybe the price is worth paying for a life. And this is some of the things that medics have to think about. It is that thing about using wisdom and applying those medical principles. So there's been now 2 successful examples of retinal malfunction being cured by gene transfer. You need to be able to get at the cells that are affected. That's the main trouble with gene therapy. Inhibitory RNA has been used to switch off localized tumors. So that's using an RNA molecule to turn a gene off. The early trumpeting of cystic fibrosis gene therapy, and that was the first disease to be tried, certainly has not yielded fruit. Temporary success. And I'm going to say a little bit about cystic fibrosis shortly. And there is this risk-benefit analysis that we've just seen with SCID. But what about germline gene therapy? What about changing a gene in the germline so that the change is inherited? That currently is illegal, as I say, in all the countries that have a framework for covering these things. But as we heard on Friday night, using mitochondrial gene transfer to cure mitochondrial diseases technically comes under germline gene therapy and is currently illegal. And so there's a big discussion about whether mitochondrial transfer should be allowed alongside somatic cell gene therapy. And then what about non-therapeutic genetic modification? Gene doping. And of course this has been Olympic and Paralympic year. And there's been a lot of discussion. There's a mouse called marathon mouse. And it runs 5 times as far as its siblings. It's had injected into its muscle stem cells a gene which is involved in the regulation of energy metabolism. So why not shoot this into a marathon runner's muscle stem cells? How about EPO, one of the proteins involved in the way we can carry oxygen in the blood? It's the protein that is controversially involved in blood doping. So we could get that into the appropriate stem cell lineage and increase the oxygen carrying capacity, all by somatic cell gene therapy. It would be against the rules of the International Olympic Association, but it would be quite hard to detect. It sat there in the genes of the person's bone marrow or muscle. And I'm going to come back to athletics later, since it is the day of the Cambridge Half Marathon. So, let me pause there a minute, and I'm now going to talk about a different sort of genetic modification. It's a genetic modification that isn't directly changing the genes, but is going to change the genetic makeup of successive generations by gene selection. And that, if you like, is engineering a lineage rather than a person. And I'm going to take you back to the mid-1970s when my wife and I were living in Nottingham, and we were part of a big group of young couples establishing our careers, starting our families and so on. And both our kids were born in Nottingham. But not one of the young couples. They were both doctors. And their first child was born fairly soon after ours and didn't thrive. And had all the symptoms that would be associated with cystic fibrosis. And it's without a genetic diagnosis, of course, it takes a little while to establish that, but the sticky secretions in the lungs and the gut, the failure to take up nutrition, all implied cystic fibrosis, and it turned out that's what it was. So my friends, Pete and Liz, both doctors, unbeknown to them, were both carriers of this recessive mutation. And in their first child, each child has a 1 in 4 chance, of course, of being homozygous, carrying 2 copies. Their first child was the 1 in 4. and was born with cystic fibrosis. Now, at that stage in the early to mid-70s, the expected lifespan for a CF child was in the teens. But as this little girl grew up, so therapy, and it really is only therapy, it's not cure, improved, and lifespan slowly extended for CF patients, although I know one who died at the age of 19. So just 4 years ago, this young woman died in her 30s, but had quite a difficult life. So that was cystic fibrosis. And this is the testimony of another person born just 1 year before our elder son. And so he's now 40, this man. And at birth, I was not expected to live much past my teens. Classic life expectancy in the early 70s for a CF child. Every day's been a battle to stay alive and defy the odds. My survival regime for the past 25 years has roughly consisted of swallowing 364,000 tablets, having 10,000 nebulizer sessions, 18,200 physiotherapy sessions, 50 intravenous treatments, 600 visits to the chemist, and 250 visits to the hospital. Tim Wootton in The Guardian. And this man sustains as normal a life as possible. He has a family, and I don't know whether they have taken steps to avoid the family having CF. He has a job, and he does as much exercise as possible. But I want to emphasize, this is not a trivial disease. And unless we regard hemochromatosis as a disease, this used to be the commonest genetic disease in Britain, with 1 in 25 of Anglo-Saxon descent being carriers, 1 in 22 of Celtic descent being carriers. Interestingly, with immigration from the Caribbean, from Africa, and from the subcontinent, sickle cell anemia is now equally common as a genetic illness in Britain. But this is the Caucasian common gene. So I'm going to then move on to 1978, test tube babies. Here is Robert Edwards and Patrick Steptoe, and that isn't Mrs. Brown. That's the nurse, the IVF nurse. Mrs. Brown was recovering from her cesarean when that picture was taken, and then he was awarded the Nobel Prize. And of course, religion came into that award because the Pope criticised the award quite strongly. And that led to the idea, combined with genetics, that we could test 8-cell embryos. And you saw a different sort of picture of testing an 8-cell embryo on Friday night. Basically, a little hole is drilled in the zona, usually with a laser, and then one cell is prized out in one way or another. And we're looking, remember, for aberrations in DNA. We can test that cell for a genetic condition by looking for some aberration in the DNA that we know about. And the cystic fibrosis gene was discovered in the late 80s and was very quickly incorporated into genetic testing. And I'm going to tell you a story now and just get you to think about this. These are not real names, they're made up, but this was the second case of genetic testing of embryos in Britain. The names are made up because they're totally anonymized in the HFEA. So they knew, for reasons of siblings, they were likely to be carriers of cystic fibrosis, both of them, and so they were both tested, and it turned out they were both carriers. They didn't want to have a child with cystic fibrosis. That would be, I think, a natural feeling when you see how serious the condition is and the lifespan. And so they underwent IVF treatment, and I want to emphasize that is no walk in the park. And they tested the embryos for cystic fibrosis, only embryos free of the mutation. And that's what the clinicians usually try to do, to have people who are homozygous, who've got 2 copies of the wild-type gene, but sometimes they have to insert an embryo that's a carrier because they're the only decent embryos you've got. But they try for homozygous wild-type, homozygous normal gene, and baby Matthew was born. So here is one of the first uses of what we call pre-implantation genetic diagnosis. And in doing that, of course, in Matthew's lineage, when he has children of his own, there will be no CF gene coming from his side of the family, whatever his partner brings. So we are engineering a genetic lineage by genetic selection. And furthermore, and this is why we think about our boundaries, we are rejecting embryos on the basis of their genotype. We're saying that these embryos do not have an acceptable genotype. Now, I think we've got time for a group discussion here. It will be quite short, but would you like to get together with your neighbour and talk about whether, in your ethical framework, this is ethically acceptable? And we'll give you like something like 90 seconds. That's all we've got really based on the clock. So maybe 2 minutes. If you haven't got a neighbour, talk to yourself. This is something we professors do quite often. Clearly, ethics committees would have spent rather longer than 2 minutes debating this. And I'm not going to ask for your views, but just leave that one sitting there whilst we go on to the next case. And again, it's the sort of case that was referred to by our two excellent speakers on Friday, but this gives us a chance to unpack it. This is a story about baby Adam, but it starts with his sister, Molly Nash, born with Fanconi anemia. Her parents, Jack and Lisa, are practicing Jews from the Ashkenazi Jewish community, where Fanconi anemia is much more frequent than in the general population of the United States. 1 in 70 are carriers. And it nearly always causes death in childhood, because what happens is that the bone marrow starts to fail when the child is 4, 5, 6, 7, that sort of age, and does not keep up the production of blood cells concomitant with the child's growth, and basically they just fail, and they generally die in their teens. However, because it's a bone marrow illness, it may be cured with a bone marrow transplant, but you've got to have a compatible donor. And just as we heard from our speakers on Friday, finding a compatible donor is often the major problem. Molly was an only child at that point, her parents were not close enough, no cousins were close enough, nothing on the donor register in the States. And so they chose to go for IVF and pre-implantation genetic diagnosis. And remember, we're looking for absence of the Fanconi mutation, and we're looking for immunocompatibility. It's called HLA typing, immunocompatibility. And I want to say this was a story that was only just successful. I'll talk about that in a moment. So Adam was born. Fortunately, I mean, we're very fortunate that the umbilical cord does have stem cells in it, and they were enough to cure Molly. And Molly is now 17 or 18, and her brother is 10 or 11. I'm not quite sure of exactly their birthdays. I think they both have birthdays in the summer. So that has been a successful story. But what can you see here that we are rejecting some embryos that are free of this illness, but aren't compatible, and so they would be healthy children, but they're not compatible. So again, a quick 2-minute discussion with your neighbour about this one. The clock is beating us here, so basically Adam was born as a saviour sibling, and one wonders. And indeed, I overheard it in the discussion here, but it was part of my talk. One wonders what would have happened if the umbilical cord cells hadn't worked, whether he would have been required, Adam, to donate bone marrow. Actually, in this particular instance, it's very unlikely that would have happened, because the story is as follows, that it took 5 rounds of IVF before there was a successful pregnancy that came to term. In 2 cases, no viable embryos were produced. In 2 cases, Lisa miscarried. And by the time Adam was born, Molly was very close to death. And during the transplant, their rabbi was present with them outside the sterile room, praying with them over a lighted candle. So they are practicing Ashkenazi Jews. And so it took much longer than they had hoped. And Molly was nearly dead when the procedure succeeded. And I think if the umbilical cord transfer hadn't succeeded, she would have died. She was that close. But now she's okay. And interestingly, Lisa, as a paediatric nurse, recognized the condition when Lisa was born. The obstetrician didn't. So, some reading. My Sister's Keeper is a novel based around that sort of issue, and Jodie Picoult wrote it on the news of this particular procedure, and then I used this story to unpack about how Christians might approach bioethical issues in an issue of third way, about 8 months ago. So, where do we go now for the last few minutes? Well, we're learning more and more about the genetics of illness, and somewhere across the world there's some 2,500 genetic tests in use. Some of them have very limited utility, actually. They tell you that you've got a 70% greater chance than normal of contracting this. So very limited utility, some of these tests, but some of them are much more direct in the way I just talked about for Fanconi and for cystic fibrosis. In the States, this is an unregulated procedure. So in a sense, there is no overarching ethical framework for genetic testing. Some of the genes have been patented, and so in those cases, the cost of the test is 3 times as much as it would be were the sequence data in the public domain. In Britain, the Human Fertilisation and Embryology Authorities license about 200 conditions, but it does include some late onset conditions like cancer of the colon, like breast cancer. These are late onset conditions. It includes some which are of lower penetrance than 100%. Again, colon cancer, about 70% of those carrying the mutation actually get the condition. And so those are allowed under our current regulations. It includes conditions which can be controlled by diet, like phenylketonuria, which all newborns incidentally are tested. But also you can, if you know that's in your family, you can now undertake IVF and PGD if you think that that is serious enough to do so. But some have not been allowed. A deaf couple were not permitted to test for genetic deafness, even though they took it to the highest court in Europe. They were still not permitted. And then we have to think about non-therapeutic interventions, genes affecting appearance and stature. Now we know that these are complex, multi-genic traits with gene interactions and environmental interactions are very, very prevalent. And so even though something like stature has got quite a high heritability, the genes contributing to that heritability are many. So it would be very hard to find one gene that you might, in order to make, you know, a basketball player or whatever. And there are these other things, these other sort of vaguer things that are part of how we present ourselves as humans individually, but nevertheless are very hard to grab genetically. Intelligence, talent, sporting prowess. And so we need to be aware of the hype that we often see in the media that we can start designing our babies. But nevertheless, and here's a little bit of Olympic year coming up. Nevertheless, we have started to, because of the interest in sports physiology that has grown up in the second half of the 20th century and right through into the 21st, we know quite a lot about the physiology, biochemistry and anatomy of what makes it possible for a person to be a particular sort of athlete. And some of those traits turn out to be relatively clear-cut genetically. I don't know about javelin throwing those. But if we just take, let's just take comparing Mo Farah with Usain Bolt, or comparing Christian Arhugu with Tiramesh Dibaba. So we've got sprinters versus distance runners here. And we know that one of the features that makes a distance runner is a high proportion of muscle fibers of the slow twitch type, where the delivery of energy from the energy synthesizing system provides for stamina rather than speed bursts. Whereas the sprinters have got a preponderance of fast twitch muscles, where the energy is delivered much faster and it enables more explosive events. It enables you to run away from the lion rather than spend days lolloping over the plain looking for the antelopes. Sort of. And we know the gene. We absolutely know the gene that causes the difference between slow twitch and fast twitch fibers. And so it's been suggested that you might want to start selecting at embryo level for the Olympics 20 years down the line now, well, actually for a distance runner 24 years down the line, for that sort of thing. Now it turns out that in terms of stamina, some 20 genetic loci have been identified where variants contribute to the ability to run with high stamina, some 20 genetic variants. And they include things like oxygen carrying capacity and that sort of thing. But the number of people who would have the ideal makeup for a distance runner, the absolutely ideal is 1 in 20 million, and I don't suppose even Mo is 1 in 20 million. So you'd be looking through a lot of embryos to get a classic world beater. And similarly, we know also about genes that regulate muscle bulk. And people have suggested that you might select an embryo in which muscle bulk was going to be greater than in a normal embryo. We know those variants, and so you might then build a 100-meter runner, or you might really go the whole hog and build a bodybuilder or a weightlifter. So these are the sorts of things. People have seriously talked about selecting at embryo level for people to be athletes. But And I don't know what makes a good pentathlete. And Jess is getting away with hitting the bar here. It didn't come off, but he is actually touching it. But you cannot make somebody an athlete by selecting their genes. How can you generate the personality and the determination of Oscar Pistorius, or the bubbly, outgoing personality of Jessica Ennis? All part of their athleticism. So although we can select genes that would enable a person to be a good athlete, we can't make an athlete. So that's why I say beware of the hype. And intelligence, well, there we are. I thought we had to put this up. This is about God and genetics. Well, here's God and cosmology. Here are two very intelligent men. And here on the left is Georges Lemaitre, a Roman Catholic priest, who was the originator of the Big Bang hypothesis. He called it the primal atom. Fred Hoyle dismissed it with some sort of Big Bang with a wave of the hand. That stuck. Two very intelligent men. Again, there is some genetic input into intelligence. There's quite a high heritability, but we cannot identify any single gene that's got more than a minor effect. So, again, beware the hype. So are we on a slippery slope? Well, I think all of us, of all religious persuasions, would agree it's a sad fact that humankind has a consistent track record in misusing God's good gifts. And if there is a slippery slope, then we jolly well better get our ice axes out fairly soon. I'm actually not a slippery slope person. I'm the sort of person who thinks ethical decisions are made by walking up to a wall and saying, should we climb over it? So there's a pause, and then we climb over it, and there's another pause. But maybe it's a question of, well, are the walls getting too easy to climb? Or maybe you think it's actually more vertical than a slippery slope. We're just about to dive off and in some way destroy our humanity. And I'm going to leave you with a couple of resources of my own. Shameless plugging. The Ethical Issues in Genetic Modification is in the bundle of papers at the back. And watch out for this next year, March 2003. I persuaded the publishers to actually put a question mark after Beyond Human. So I'm questioning whether these sorts of technologies are in some way transcending our human condition, or whether they're simply part of what humans do. Okay, thank you very much.
Thank you very much, John. Well, I'm sure that stimulated plenty of questions and points for discussion, so over to you.
So towards the beginning you articulated the ethical challenges balanced with what seemed to me sort of medical and economic benefits of a given, for example,
yes,
reproductive technology. And I wonder if you would agree, and so this is sort of let me unpack this. My understanding of the initial experiments that say, John, we talked about it a little bit the other day, John Gurdon
yes,
was undertaking in the 50s, and this regards with nuclear transfer and how that relates to cloning ultimately. And it seems to me that basic technology is really what's going on in terms of some of the mitochondrial defects that we heard about on Friday evening. So the question is, back at that time, what was motivating that research had nothing to do with economic or reproductive benefits. It was the purely academic question, does every cell in the body have the same copy of DNA? And thus, when one phrases is this ethical challenge worth pursuing for some economic or medical benefit? Can I convince you, or I'm probably breaking open doors, but wouldn't you agree that you wouldn't necessarily want to phrase it like that, and rather one would want to phrase the benefits in terms of just because we're curious about it, that's enough?
Yes. I mean, you are pushing at an open door here. Basically, Robert is asking whether it's the basic scientific motivation that we should be looking at and evaluating. And I agree with you. Gurdon's experiments were done to look at totipotency, the idea that all cells in the adult body retain the full gene set. And indeed, when I talk to my students before the birth of Dolly, talking to first-year students about developmental biology, I would always say this has not yet been achieved with the mammal, but the first group that does so will deserve a Nobel Prize. That's what I said. And what happened is they got, I was about to say something rude, they received the opprobrium of the world instead of praise. And it showed that mammals could be treated in those terms in the same way as amphibians. So the pure science to me is important, and that's why I put up the picture of the blue sky, because I think my own view of the ethics of science research is that no area of knowledge is off limits, but some of the methods that we might want to use to get there are off limits. But the applications of science raise the ethical issues. It's not the science per se. I'm not saying that science is free of social construction, because it isn't. There is quite a lot of social element in what we do. But nevertheless, the ethical problems and issues come with how we use the knowledge, not with the knowledge itself.
Please, yes.
You did say that the big question is, what is the value of the embryo? And I think this is a very important thing, but are we ever going to come to an agreement between those who are believers and those who are just simply scientists?
So what is the value of the embryo? In fact, I phrased it slightly more differently. I said, should the embryo come within our moral boundaries? But that, I guess, is saying the same thing. Do we accord to the embryo the status of a person, and therefore treat it as a person, loving it as my neighbour in the Christian ethic, doing unto it as I would be done by in the Victorian Golden Rule and so on. And I have to say that it's not a question of people of faith versus people of no faith. It simply isn't, because there are many of us in the faith community who do not regard the early embryo as a person. I'm one of them. That doesn't mean to say that I think the embryo is a commodity, but nevertheless, so it's a different sort of moral awareness that I'm treating the embryo. But I do not regard the early human embryo as a person. And within the faith communities, there are quite a few people who think like me. We are mostly scientists and medics, but not entirely. So the theologian Ted Peters would agree with my standpoint. So there are different, and also outside the faith communities, there are those who want to treat the early embryo as a person. So it isn't a clear-cut division.
Please, yes.
Along the same line that you were giving two examples of two case studies, so to say, and certain embryos were chosen and certain others were tested.
Rejected,
for.
yes. That's
So now what would be the, I'm just sort of thinking loud here, what would be the ethical underlying principles that one can employ as to choose some to be good, to be utilitarian, so to say, or to be fulfilling the needs of a family, rather than others which are not?
Okay, so I'm going to talk to you about two Christian thinkers now, but the same will apply, I'm sure, in the world of Judaism, Islam, and probably Hinduism too. That the theologian Ted Peters says that Christians are required to love their neighbour as themselves, and loving their neighbour will be to treat them as best as you can. And in his particular case, the neighbour are the prospective parents. And he says the same incident about use of stem cells, but the neighbour are the prospective parents. And so we try to care for them, to enable them to have a child who is free from a serious genetic condition. On the other hand, Philip Taylor of Care for the Family argues that the neighbour is the embryo, because it is a human person. And therefore we care for the embryo as if it ourselves, never mind the parents. That's almost a deontological position. You know, you care for the embryo, whatever the outcome, and therefore you don't undertake this sort of work at all. So those are the two ways of looking at it, and you know, it's quite hard to steer a middle course between those two.
I was just wondering if telos, I mean the aim that we want to achieve in human society,
Yeah.
if we consider well-being of human society as the goal towards which that beatification can be achieved. I mean, it's going to be a big idea for Christians as well. If that is the case, then this kind of research, whether this can be encouraged. What would it?
My own view on this is that, having seen the outcome of children born with serious, incurable genetic conditions, then I would say, for the sake of the health of human society, these techniques of pre-implantation diagnosis are acceptable. Where I begin to worry, and I just mentioned it quickly in passing, are where the disease is late onset, coming much later in life, where there is not 100% penetrance, where you're not sure you're going to get the disease, and where in some cases there is actually a significant cure rate. And I did mention cancer of the bowel, colon cancer, and remember that the majority of colon cancer cases are sporadic and not genetic. But in the genetic case of colon cancer, it comes in when the person is in their 50s usually. 70% penetrance, so 30% of the possessors of that mutation don't get it. And then with early screening and early detection, there's a 90% cure rate. My brother-in-law had colon cancer 15 years ago, and he's fine because it's detected early. He had the sporadic form. So when we come to those sorts of conditions, I'm just wondering whether we have gone too far in looking after the family rather than regarding the embryo. So you can see it is quite a difficult path to weed. And then we come to something like phenylketonuria, the inability to metabolize the amino acid phenylalanine, which if we allow that to run for more than a few days will start to cause mental retardation. And for that reason, since the Second World War, the biochemistry of that disease has been well known, and all babies in Britain and in many other countries have been subjected to a heel prick test where a drop of blood is taken, and the diet is changed immediately. Now the diet is rather boring, but you know, I know somebody with phenylketonuria who's now in his 70s, has had a boring diet, but otherwise a good life. And I was quite surprised, actually, when the Human Fertilisation Embryology Authority added that to their list of licensed conditions. And so I'm beginning to say that maybe just the way we're using this technology is beginning to devalue the human embryo. Even though I don't regard the human embryo as a human person, I don't regard it as just a trivial ball of cells, because it has the potential in a pregnancy, in some pregnancies, to become a human being, to become a human person. So, you know, we're trying. What I'm trying to do is to apply virtue to this situation. I try to act as a virtue ethicist. I'm saying that for me there are not black and white rules in this area. So I'm trying to apply wisdom and compassion and love. I may not be doing it very well, but that's what I'm trying to do.
Please, Edmund. Yes.
I was thinking about another case study. A couple of months ago, I saw the article about parents in the US. They were deafness, you know.
Yes, deafness.
Yeah, sorry for my English. And
It's okay.
they want to have a child.
Yes.
That child with deafness too. What about this situation? It's only our point of normality, or we should, you know, consider autonomy of parents.
This is a very good point, and not just in the United States, where the selection was allowed, but in Britain too, where the selection was not allowed. So let me tell you a little bit about the case. Sometimes I throw it in as a case study in these talks, mainly for school students who get really quite noisy about this particular case study. Two parents in Britain, they were both congenitally deaf. In other words, their deafness was caused by a genetic condition. They were both in theatre for the disabled. One was a very able theatre director. He was called, unlikely, Tomato. So when I'm talking to school students about him, I call him Tom. And he otherwise, chaos.
Yes.
And his wife, Paula. And their first child, incidentally called Molly, just like Molly Nash, their first child was deaf. She'd inherited the deafness. They wanted to have a second child. They wanted to make sure that that child was also deaf. And so they applied to their local clinic for testing for the relevant genetic makeup in an embryo. But if you look at the Human Fertilisation and Embryology Authority guidelines, there's a very clear statement that testing shall not be done to favour or to select for conditions that are regarded as disabilities or disadvantages. So they were refused that. Now, Tom and Paula came back to the HFEA and said, but look, in the deaf community, deafness is not a disability, particularly as British Sign Language has now been is now an official language, the sign language with which deaf people communicate with each other. But the HFA would not budge. They said, okay, within your community, that's fine. but outside your community, however inclusive we are, and wanting to include disabled people in everything we do, it's nevertheless a disability. And having had a profoundly deaf student graduate from my department, I think I have to agree with that. It's very hard for communication for that student. And so they took it to the highest court in Britain, who also turned them down. They then took it to the European Court of Justice, who also have recently turned them down. And so it has not been allowed in Britain because of this clause about favouring a disability is not permitted. Now, I don't know how you feel about that. I don't know how the audience would feel about that. But that's the situation. Anybody got any thoughts on that?
A good judgment. Not to favour the probation of a child, as to say.
When we were starting our family, another one of the families we came across, they weren't part of our little friendship group, but just down the road from one of our friends, couple friends, was a blind couple who had a sighted child. And that must have been quite interesting for the child.
Okay, I think there's a question at the back. No? Yes?
It's more of a comment, really. If you're talking about pre-implantation diagnosis and you're talking about selection on the basis of genotype, to a certain extent, being pragmatic first, if you are going through an IVF procedure, let's assume for reasons of subfertility, let's say 10 embryos are created, you're not going to implant all 10 into a uterus. So there's a level of selection going on there, and this selection is the embryologist looking down a microscope and saying, okay, well, of these 10 embryos, that one is definitely out, that one looks awful. But from the other 9, it might just come down to that gut feeling of the embryologist. I quite like the look of this one. I quite like the look of this one. I'm going to select these two. So there is selection going on. Is pre-implantation diagnosis not just a slightly more scientific form of selection?
I agree with you entirely that the embryologist uses embryo phenotype, what it looks like, in order to judge whether it's worth. There is now a method of doing chromosome typing also on embryos that is less invasive, but that's a new development. But yes, that's what happens. So embryos are rejected, and it's quite interesting that some people have, and I'm going to phrase this, and this isn't a pejorative term. Some people of more fundamentalist Christian faith who have undergone IVF have asked for just one embryo to be created for that reason, and whatever it looks like, to try to start a pregnancy with it. And of course, actually, if the embryo is malformed, the pregnancy won't work anyway. So, and I know 1 or 2 couples who've gone down that road.
What does that do for the success rate?
It knocks it way down because if you've got 8 embryos in a dish, and some of them are bound to be quite good looking, they usually, in the old days, they implanted 3, and that was taken down to 2 when Susie Leather became chair of the HFA, and they're now taking that down to 1 because when multiple pregnancies are established, there was this terrible thing about selective abortion of the extra child, extra fetus. So they now do 1. The success rate now using 1 implanted embryo is somewhere around 20-25% per round of IVF, provided the mother's under 35. And I mean, they said 39, but in fact most local authorities now use 35 as their cut-off point. But obviously, if you're only using 1 embryo, then whatever it's like, you've got to try to start a pregnancy with it.
John, just to clarify a figure that was mentioned, I mean, I think usually people say if you take every fertilized egg, the chances of it coming to full term and there being a baby is something like, 70%, it's like 30%. Something
It's
like that.
smaller than that, actually.
Well, I was going to ask you on this because I've heard various figures and I wonder what figure you would come up with and how, where are the data for that? Actually, where are the data sitting?
Well, the trouble is the data all reaches by kind of hearsay, don't they? But
Yeah.
it is widely said that only 30% of fertilized eggs start a pregnancy.
Mm-hmm.
And once implantation has occurred, then, if you like, the body treats the growing organism more seriously, and so later and later miscarriages are rarer and rarer. So it may be as high as 20-25% of fertilized eggs.
That make it to term.
Make it,
Yes.
yes. Maybe I think we also ought to put this in a number context. That of the many, many births we have in Britain every year, some 12,000 have arisen through IVF. And it's been fairly stable. It plateaued about 10 years ago, and it's been fairly stable ever since. About 200 to 300 in a given year have come through pre-implantation genetic diagnosis. You can get these data from the HFEA. So there's a kind of running mean of somewhere over 200 have come through the procedure we've described today. So it's a small proportion. And when it comes to Saviour siblings, as our colleague said on Friday, every single case, Saviour sibling, child born to Saviour donor, every single case has to present itself by the clinician to the HFEA. And since the first one was allowed in 2004 in Britain, there have been less than 10. It may even be less than 5. And some of those are quite tragic. There's a little boy dying of thalassemia. His mother's miscarried 5 times now with the implanted embryo. So they're very small in number. It's a tiny handful of Saviour siblings, 200 to 300 genetically selected embryos. And as I said in my question on Friday, that is far, far lower than the couples who are at risk of having a child with a serious genetic condition. And it is this business, I think, that IVF is a very invasive and uncomfortable procedure. You just need to read Lisa Nash's account of them trying to have a baby to know how difficult it can be. So I suspect that IVF and PGD as an option is not popular because of the IVF procedure itself.
There was a question somewhere. There was one here, and then we'll go with this. Yeah.
I would like to know what you think about rejecting an embryo that might lead to a very severe disease and letting a family get this kid who is sick. They have 5-6 years of a really hard time, and then the kid dies.
Mm-hmm.
Isn't it harder to lose that kid while you've got feelings for it, you love that baby, and
Yeah, you're talking about Tay-Sachs disease, for example, another disease of Ashkenazi Jews.
and on the other hand, take away an embryo that you don't really know yet.
I'm with you. That, my own view there is that pre-implantation selection is acceptable. The Ashkenazi Jewish communities had other ways of dealing with Tay-Sachs. That the rabbi is in Chicago, New York, kept a record of the genotype of all young persons, and it was anonymized, so only he could decode it. And when 2 young people fell in love, or in traditional communities were brought together by the matchmaker, and that still happens, their records were looked up, and if they both had the Tay-Sachs mutation, were both carriers, they were advised not to marry or not to have children, or whatever. And the incidence of Tay-Sachs has gone way, way down in these communities since the gene test has been available. It's been called eugenics with a smiling face. But since pre-implantation diagnosis came on stream, it would be very interesting to know whether couples with the mutation were marrying and having children and were using PGD. That I don't know. So there are other ways of lowering the incidence of a genotype in the population.
This wasn't going to be my question, but following on from that, this isn't about gene modification particularly, but one of my daughters works in Great Ormond Street, the High Dependency Unit, which was featured in a number of television programs recently. And one of the big problems is, as a colleague was saying, that once the baby with deformity is born, the parents love it, and they want it to survive. So it's a tremendous problem in not being able to let go of that child. The net result of that, though, is you have a huge resource problem. These children that can only be kept alive with exquisitely high-cost technology, and it actually means other people can't get the treatment. So there might be an issue, perhaps within genetic modification, of a justice issue. But my real question was going to be, could we be altering the gene pool anyway by modern medical practice, which is allowing the survival of people with chronic diseases which may have some heritability, like early onset diabetes, intermittent diabetes. So could we in fact be altering the gene pool anyway by better medicine? Not necessarily for the best in some respects. I'm not saying, by the way, that I think people with diabetes should not reproduce, don't get me wrong, but are we not already manipulating the gene pool?
Yeah, and of course, only a small proportion of diabetes cases are heritable.
Yeah.
Although at least one type clearly is. Yes, I think we are altering the gene pool, but it's not, if you like, in a measurable manner. You know, we're not seeing a great blip appearing on the boundaries of our gene pool. We are undoubtedly altering it in a small way, but I agree with you. That doesn't mean to say that we shouldn't use interventive medicine where possible. But one of the interesting things about the programs about Great Ormond Street was one of the paediatric surgeons saying of particularly heroic interventions which were not necessarily going to work. He said, sometimes I wish I had the courage to tell the parents, we will not do this because it's not going to bring any benefit to the child at all.
Yes, yes. But because of patient autonomy, or
but exactly, patient autonomy
it's very difficult to
the
say that. I found myself saying to my daughter, why don't you just say that your child is very, very sick? You know, and make it quite but you can't do that with these consultations.
Why not?
Well, because of autonomy.
Individualism and autonomy has become one of the key ways in which society functions.
I think there's a philosophical thing that we see more now in which people are saying, it should not die, he should not die, we will prevent death.
Yes. It's in the book. Chapter 7. The chapter's called Gamete to Grave. I find it interesting that nobody's raising questions about synthetic biology here. Perhaps they've forgotten all about that. I'm just going to go and make an organism whilst you're chatting.
Just to comment a little bit on that last point as well, because some people would say, you know, that the teaching, the ethical teaching of Jesus and of course other religious teachings are stopping human evolution. I mean, people often ask, you know, is human evolution continuing? Well, I mean, one answer to that is that, of course, we're doing everything possible to keep people alive to reproductive age, you know, in a way that simply wasn't, that's removing a lot of selection pressure that was there even, you know, 100 years ago in this country, certainly. So in a way, we're preventing, you know, allowing this wonderful proliferation of lots of genetic diversity that might not have been there before. So the other thing to remember, actually, is I think I mentioned this yesterday, but this is quite recent data, that the average, you know, if you look at a newborn baby, there's somewhere between 40, and, as I said, depending on the age of the father, there's somewhere between 40 and 60 new novel mutations in that baby that were not present in either of the parents.
Yes.
That's pretty high. I mean, that's much higher than I'd ever thought. This has really only been out a few weeks, actually. So, and it's based on just sequencing a lot of genomes.
And because it's partly because spermatogenesis carries on throughout the life of the male, and as we age, so our repair mechanisms decline and so on. Whereas, of course, ovaries have produced most of the eggs that are ever going to be used.
Yeah. Okay, Robert, and then we'll...
Just very quickly,
Yes.
the telomeres get longer. So apparently the lifespan of children of older males tends to be...
How interesting. Telomeres are the bits on the ends of chromosomes that stop them fraying, and during our lifespan they shorten, and that's one of the means by which our cells age. So the telomeres are longer in the spermatozoa of older males.
With Google, I can find the paper. It's very because I appreciate that there's some uncertainty, but my understanding was that during spermatogenesis, there's a difference when you're young and when you're old, of course. And you know, apparently the heritability of lifespan is positive the older.
So you could be a long-lived mutant. That's what it is. But remember, we are all mutants, actually, and that's a serious point. Each of us are carrying about 10 or a dozen heterozygous allelic changes, which if we were homozygous, had both copies, would be dead by now, probably in the embryo. So.
Yeah, good to have paired chromosomes.
Yes, absolutely.
Well, with that thought, I think we better have a coffee and tea. But let's thank John very much for your thoughts.